a product consultant and also the Daylight team manager at 475. I've been with the company now for about 7.5 years, and for most of that time, I have been working within the Daylight department. I've also spent some time throughout my professional career teaching at City College, a course on low energy buildings and high performance architecture, basically an introduction to sustainability in construction and net zero and passive house style buildings for architecture and sustainability students. So these issues and the topics that we're going to talk about today and the 475 supports in general are something that I'm very passionate about. I'm also joined today by my colleague Delia, who is the customer service representative for our Daylight products, these skylights that 475 supplies. She'll be in the chat. If you have any questions, feel free to drop them in. Also make some time at the end of the presentation to answer any questions. So for most of you here today, I imagine you've been to our website, but if not, I highly recommend checking it out. It is a great resource to learn more about any of our products, including our skylight products. It also offers a variety of knowledge resources, including our smart enclosure ebooks and CAD details, which are available for free download on the 475 website, and demonstrate our best practice recommendations for high performance enclosure details in a variety of different building typologies, incorporating our products to different degrees, depending on the energy goals of a given product or project, I should say. At 475, we supply a variety of different solutions: air and vapor control through Proclima and Stego, insulation through a German manufacturer Gutex of wood fiberboard insulation products. And then also when we build to a very high degree of air tightness, we need to ventilate mechanically. So 475 supplies centralized ERV systems through Brink, which we'll be presenting on next month, and then also decentralized HRV solutions through Lunos. But today I'm here to talk to you about our roof daylighting product specifically. To learn more about our roof daylighting products and to see a variety of different photos, project examples, blog posts, etc., I recommend checking out our Daylight website, 475daylight.com. I'll get into a little bit more about these products towards the end of the presentation, introduced via case study on our new headquarters. But for now, I just want to give you the URL here and encourage you all to check out the website when you have a chance. So, getting into the presentation, high performance roof daylighting. As a starting point, we like to sort of define some of the terms that we'll be using frequently in this presentation. So starting with high performance, something that we reference very often, something that is in our company name, but something that's kind of vague in general. So generally speaking, when I give this presentation, I like to open it up to the group at this point and just ask you guys to give some characteristics of what you would expect from a high performance building. If you are so motivated, you can do so in the chat and I'll call out some of your answers. So what are some characteristics of high performance buildings? Well, 475, some of the characteristics that we expect from high performance buildings are listed here. I see Vincent in the chat mentioned no leaks. No leaks is a big one. Both water control, stopping water leakage, which would affect the durability of the structure. Also, of course, air leaks, preventing drafts and air leaks through very high degrees of air tightness is the most effective way that we can reduce our heating and cooling demands. Reducing air leaks will also have disproportionate effects on vapor control and thermal control. So yes, no leaks is definitely something that our company advocates for strongly. Eliminating leaks and also insulating continuously will also provide for very high levels of comfort. So high performance buildings are generally very comfortable when we reduce or eliminate drafts and have continuous insulation with minimal thermal bridges. We have very consistent interior surface temperatures, eliminating cold spots and temperature asymmetry, and creating a very comfortable interior. In addition, because these high performance buildings provide a very high level of air tightness, we're able to regulate very intentionally how much air enters and exits into our building, and we're able to bring that air in through our mechanical ventilation system, thereby continuously filtering that air while also exhausting stale air. So these buildings generally have very high indoor air quality and have more healthy interiors for that reason. Perhaps an obvious one, but energy efficient is definitely something that high performance buildings offer. When we do air seal continuously and insulate continuously, we're mitigating heat transfer through the enclosure, which reduces strain on our mechanical heating and cooling systems. High performance buildings are very resilient because they do provide such excellent control over water, air, vapor, and temperature, heat transfer. We are able to reduce the amount of heat gain and heat loss that occurs throughout the year, and thereby, again, reduce our operational energy requirements. These buildings can be very resilient for many of the same reasons, because they generally are preventing or reducing the impact of the elements on the enclosure, They are built to last for the long term, which is critical for sustainable building because the most sustainable building is an existing one. We want to be building structures that are going to last for the next 100 years or more to reduce the embodied energy of having to bring in new materials to recreate these structures. Somewhat controversial, perhaps, characteristic of high performance buildings is affordability, but we definitely believe that there's no reason that high performance buildings can't be affordable, particularly air tightness, which I mentioned already a couple times, can be implemented on most projects without having a significant impact on the budget. So we do believe that these buildings can be affordable in many applications. And then beautiful, there's no reason that high performance buildings can't be beautiful. All of the principles that we advocate for, the passive house principles that our companies stand behind, can be implemented in any structure, any geometry, any design for the most part. And for that reason, there's no reason that high performance buildings need to be limited in their design. So there are various different components of high performance buildings that allow us to get these high performance results. You can see them listed here on the slide. But today I'm going to talk primarily about quality daylighting. So let's go ahead and define that term in our next slide here. So at 475, we define quality daylighting according to several different characteristics, which you see listed here, and which I think are summed up really nicely in this photograph, which features two children of 475 founding member Ken Levinson sitting here at a windowsill in a brownstone in Brooklyn. We can see that these two children are quite comfortable in this windowsill, despite the fact that the exterior temperatures are obviously quite cold. Here they are sitting in their pajamas with no shoes and no socks on, without necessarily needing additional layers to feel comfortable in the space. We can see that the snow from the exterior is right up against the glass and hasn't melted yet. This is an indication that there's not much heat transfer occurring through the fenestration, both the glass and the frame, an indicator that this window solution is thermally continuous, thermally broken. And finally, we can see these children are reading by the natural light provided through this fenestration, the window in this case, which is indicating that we've optimized our illumination from natural light to reduce our electrical demands and to provide comfortable levels of natural light at the interior. So just defining some of these elements of quality daylighting quickly. One, we want to ensure when we are designing for quality daylighting that we have a balanced window to wall ratio. Anytime that we put a penetration in our enclosure, whether it's for a window or a door or a skylight, which we're going to talk a lot about today, we are inherently weakening the thermal performance of this enclosure. This is because fenestration will almost never be able to have as low of a U value or as high of an R value as the surrounding opaque structure. So we want to be very intentional in how we're locating our fenestration, how we're sizing our fenestration, and be considerate of the impact that this will have on the overall thermal performance of our building. In addition, we want to be optimizing our fenestration to allow for illumination from natural light in order to offset our electrical demands, and then also optimizing our fenestration to allow for solar gains or solar radiation, which will help, again, offset our heating demands. In New York City, we're in a heating-dominated climate, so by offsetting our heating demand using natural light, we can greatly reduce the overall heating demand and thereby carbon footprint of our buildings. Another characteristic of quality daylighting is fenestration solutions that are thermally continuous or continuously insulated with minimal thermal bridging, and fenestration solutions that are airtight and that won't compromise the airtightness of the enclosure. Finally, for quality daylighting, we want to be considering the effect of over-illumination, glare, and overheating. We want to be utilizing diffusion elements or shading where necessary to reduce visual and discomfort that might occur due to that over-illumination. So based on these characteristics that we've defined for quality daylighting, would you guys say that this is a good example of quality daylighting based on this photo? I see someone in the chat answered no, it's not a great example of quality daylighting, and I would agree. Not a great photo here, but I do think it does a nice job here of introducing this point. In this photo, we can see that a significant portion of the enclosure has been opened up for this sloped glazing fenestration element. So we can assume that the thermal performance of the enclosure has been compromised to a significant extent in order to allow for natural light, illumination, and solar radiation to reach the interior. Yet despite the fact that we've opened up such a significant portion of our enclosure and compromised our window to wall ratio to such a great extent, we can see that the effect that this natural light has is not ideal. How we can see this is that the retail spaces below the sloped glazing still are very reliant on natural or on electrical illumination to illuminate their spaces. And so for that reason, we can also assume that we're probably not getting much solar radiation or solar gains in addition to a lack of natural illumination. So why do we utilize daylighting in architecture and construction? There are a variety of different benefits, but they certainly, one of them are health and productivity for our tenants. As human beings, uh, we are very in tune with our circadian rhythm. The circadian rhythm allows us to feel more energized during the day and to sleep better at night, and is largely reliant on the pattern of the sun throughout the day and the pattern of light throughout the day in order to be reinforced effectively. So when we have natural light, our access to natural light in our day to day, we'll feel more energized at work, we'll feel more rested at night, and it'll definitely benefit us physically and cognitively. In addition, there are various examples of the benefits of natural light, such as students that have access to natural light during exams are shown to be more attentive or shown to perform better in terms of the results that they receive. Shoppers at retail locations that have access to natural light tend to spend more time in store. They also tend to spend more on products. This is partially because of the pleasantness of shopping in a place that has access to natural light, and partially because natural light allows us to see the full spectrum of visible light, which allows us to more accurately visualize the colors that are being represented in a given product. This same quality of natural light and its ability to allow us to visualize the full spectrum of visible light also creates excellent aesthetic and architectural benefits. Natural light allows us to capture very specific qualities of light within a space and really give a space a specific feel based on how we introduced natural light into that space. So we can see a cool example here, the Kimball Art Museum by Louis Kahn, which features a very long, narrow skylight at the ridge of this concrete bow roof. We can see there's a diffusion element at the interior, reflecting that natural light back to the ceiling, allowing for light-filled space, naturally illuminated, without allowing that light and thereby the UV to come into contact with these paintings below, which could degrade them over time. In addition to these health and design benefits, daylighting also can have the benefit of energy savings. As many of you already know, I'm sure, and seen many of these past house presentations, heat transfer occurs through our buildings and through our fenestration in three primary ways. Convection, which is heat transfer via airflow or air leaks. Conduction, which is heat flow through a material via heat transfer. And then radiation, which is heat transfer from the sun, basically solar gains that are coming through primarily our fenestration, our windows, our doors, and our skylights. So when we consider our energy balance being the sum of all of our heat gains, with all of our heat losses then deducted, if we are able to reduce convection and conduction to a certain extent, while also capturing the heat gain from radiation, we can get to a point, particularly in the winter, where we are able to offset our heating demand partially using the free heat or solar radiation from the sun. I'll give a little example, or a little energy balance case study at the end of the presentation, which will demonstrate this point in more detail. So why roof daylighting specifically? Well, roof daylighting skylights are ideally positioned to capitalize on the benefits that we've already discussed: health and productivity, aesthetic and design, and energy savings. Because they're positioned on the roof, they're oriented directly towards the open sky, and so they receive much more direct daylight and much more light in general throughout the day and throughout the year. In addition, skylights in particular are well suited to capitalize on the benefits of natural ventilation, both by taking advantage of the stack effect or the tendency of warm air to rise in our buildings when it's able to escape from higher stories, and then also capitalize on the benefits of nighttime flushing, particularly relevant in shoulder seasons to flush heat at night and for reset, so to speak, for our mechanical systems when the space is in use the next day. Finally, skylights, particularly in urban applications, are ideally suited to allow for exterior access via opening up towards the roof, which could be difficult to achieve in particular urban locations without providing that access. So here we have a nice image of a BuildingBlocks product, the Comfort Swing, which is featured on our office here at 475. I'll talk a little bit more about this product later in the presentation. But essentially, because of this product, we have access to our roof deck. We have a connection to the outdoors that we would not be able to achieve without a roof daylighting element. So look a little bit closer at the relationship between skylights and windows. Because, as I mentioned, skylights are positioned towards the open sky, they are better situated to receive direct light and more illumination and heat throughout the day and throughout the year. For this reason, skylights can be much smaller than windows while still capturing similar amounts of light. In the image on the right, we can see the illumination from the open sky in various different weather conditions. On a direct sunny day, we can see that illumination is typically measured at 5,000 to 10,000 foot candles from the open sky. But even on a stormy, dark, heavily clouded day, we still get illumination from the open sky around 1,000 foot candles. When we consider that office work typically requires less than 100-foot candles to complete comfortably, we can conclude that skylights are able to provide adequate illumination to significantly impact our electrical demands and thereby the energy usage of our buildings. Windows, generally speaking, or I guess as a rule of thumb, we like to say that windows allow for light to penetrate about 2 times the head height of the window into the interior space. So in the image in the top here, top right, you can see a window in an open space, and that window is allowing for some natural illumination, but primarily in the spaces directly adjacent to that window. If we add a clear story or a light shelf to the window, we can reflect light deeper into the space, about 2.5 times the head height of the window approximately. But we're still not able to evenly illuminate the space as much as we might want to. People directly adjacent to this window will have great access to the natural light, but as we get deeper into the space and further from our exterior walls, that natural illumination will not be as present. When we utilize skylights evenly throughout a space, particularly when we utilize splayed light wells or curbs that might allow that light to penetrate deeper into the interior, we can see that we're able to evenly distribute light throughout the interior, even to spaces that might not be directly adjacent to an exterior wall. So skylights can allow for natural light to reach spaces that might otherwise be difficult to achieve. However, there are certainly common problems associated with roof daylighting. Because they do get so much direct light, they are susceptible to over illumination or glare, which can create visual discomfort and make it difficult to complete work comfortably or even to just rest comfortably. In addition, this exposure can create overheating, particularly in the summer, as we gain solar radiation that can negatively impact our cooling demands. In addition, if our skylight solutions are not thermally broken, we have very warm exterior temperatures in the summer. That heat can be transferred inward, which will also have an impact on the interior comfort and cooling demands. In the winter, we can see the opposite effect where we have very cold exterior temperatures. If our skylight is not thermally broken, we can see heat rise to our ceiling level and then be transferred outward via the skylight assembly. What can occur when the exterior temperatures are quite cold is condensation, as the interior surfaces of a skylight can become quite cold when the solution is not thermally broken, as we're spending all of our time or most of our time in the winter indoors, cooking, cleaning, showering, breathing. We're generating lots of moisture. This warm, moist air at the interior will rise again. It'll come into contact with this cold interior surface of the skylight and can then condense and create condensation, sometimes perceived as a leak, but often this moisture is in fact due to the effects of heat transfer and thermal bridging. So looking a little bit closer at some of these comfort drivers, first, uniform surface temperatures. Here we see an example from Nick Grant. He was in his office and the air temperature in his office was 23 degrees Celsius, which is a little warm, but right around room temperature. However, Nick felt like there was a radiator on in the space and he couldn't figure out why. So he took out this thermal imaging camera and he photographed the skylight on the left and the windows on the right. And what he realized is that the interior surface temperatures of these fenestration elements were much warmer than the surrounding air temperatures. This is because we're most likely in the summer season here, so the exterior temperatures are very warm. And because the skylight and these windows are not thermally broken, that heat from the exterior is being transferred inward. And when that occurs, the interior surfaces of the fenestration, skylight and windows becomes much warmer than the interior air temperature. And that heat from the interior surfaces of the fenestration will actually radiate inward and create this effect of a radiator or of a heat source. Here we can see that the interior surface temperatures of these fenestration elements were measured at 50 degrees Celsius and just below that number, which is almost twice as warm, or temperature is twice as high as the air temperature in that space. So problematic for comfort and then also for energy usage. Looking a little bit further at this phenomenon, we can see two examples here, two small buildings with a little person inside. And the building on the left, we can see that the enclosure is not robustly insulated, we'll say. And we'll assume in this example on the left that the window shown on the right of our little building is double glazed and not thermally broken. The exterior temperatures in this example are quite cold at 6 degrees Fahrenheit, and we're conditioning the interior to around 68 degrees Fahrenheit. However, again, because of heat transfer through our window in this case, the interior surfaces of this window will become quite cold. In this example, they're measured at 59 degrees Fahrenheit for the interior surface temperatures of the window. And as our warm conditioned air comes into contact with the cold interior surface of this window, it'll cool and it'll sink, and the vacuum that air leaves behind will be filled by more warm air. And as this warm air cools and sinks and circulates throughout our space, it'll create a feeling of draftiness or convective looping, even though it's possible that there's no convection or air transfer occurring. It's just this phenomenon due to imbalance in the relationship between air temperature and surface temperature. In the example on the right, we can see that we've added more insulation to our enclosure. We're going to assume here that we've installed now a thermally broken window with triple layer glazing. And so the interior surface temperatures of that window, despite the cold exterior temperatures, are going to remain much more similar to the interior air temperature. Now we've eliminated or reduced significantly the difference between the air temperature and the interior surface temperature of the windows, and we've reduced or eliminated the impact of convective looping and that feeling of draftiness. I want to talk a little bit about design considerations for skylights and fenestration in general. Starting with detailing here. Fenestration, skylights, windows, doors are unique in that they're really the only element or component in our enclosure that's providing for all four control layers. So getting into those control layers a little bit, in order of importance, they are water control. If we can't prevent water leakage or water from entering into our structure and into our interior, then our buildings are going to be barely habitable. They're not going to be durable or built to last. And they're really not going to be serving their primary purpose. After water control, air control is of the next most importance because we just mentioned at the beginning of the presentation, air control is going to have the most significant impact on our heating and cooling demand and will also disproportionately affect vapor and thermal control. After air control is vapor control in terms of order of importance. We're not going to get too much into vapor control in this presentation because fenestration is typically vapor closed. Vapor movement is not a big factor once we've eliminated air movement. However, we do want to be considerate of thermal control and how we are connecting our thermal control in our enclosures, in our opaque assemblies to our fenestration to provide for thermal continuity and to minimize thermal bridging. So what's nice about the landmark skylights specifically that we supply is that they're available with insulated curbs as part of their assembly. What this insulated curb allows for is very simple and intuitive detailing for connection of the control layers in our roof to our skylight. As we can see in this section drawing on the right, the insulated curb of the skylight is set down on the roof deck or sheathing, and the exterior insulation just outboard of that sheathing is then run directly into the side of the landmark's curb. This will ensure that the thermal control is continuous from the roof to the skylight curb, and then since the landmark skylights are thermally continuous with insulation at their frames and then warm edge spacers and then triple layer glazing, we can be confident that the thermal continuity will continue over the full roof opening. This blue line that you can see at the exterior of the section drawing is a roofing membrane or a primary flashing control layer or water control layer. This roofing membrane runs from the roof and can be connected directly to the side of the curb, terminating about 1 inch from the top of the curb, just underneath the skylight's drip edge. That will ensure that we are continuously watertight from the roof to the skylight assembly. And since these skylights are extremely airtight, extremely watertight, we can be very confident that our install will perform and provide for water control throughout the lifetime of the product. At the interior, which is 475's recommended location for an air control layer, you can see that the Intello Plus is specified and called out with this red line running at the ceiling up to the base of the skylight. Again, because these skylights are airtight and because we have this insulated curb, all we have to do to ensure continuity of air control between the roof and the skylight is connect our air control layer, in this case, again, the Intello Plus airtight membrane, to our curb at any location. In this example, we've shown it at the base of the curb, which is to ensure that it can be concealed by the interior trim. And it's probably connected at a location with Tescon Vanna tape or some sort of adhesive. So looking a little bit closer at thermal control specifically, when it comes to thermal control, placement and alignment really matters. Here we're looking at an example of a window installed in the same wall assembly, installed in 3 different positions within that wall assembly. For this example, we're going to assume that the thermal control layer or the insulation layer is centered in our wall assembly. And so we want to align the thermal control layer in our window, which is in this case, the window assembly itself, assumed to be thermally continuous, with the thermal control layer or insulation in the surrounding wall. So in the image on the left, we can see this is a thermal model. So each color shown here represents a different temperature strata. And we're basically looking for any indicators that thermal bridging is occurring, which would be shown by colors kinking or bleeding or moving through this wall assembly in this window. So in this example on the left, where the window is installed outboard in the wall assembly, we can see that there is some heat transfer occurring between the thermally continuous window and the thermal control in the wall assembly because the window is out of alignment with that thermal control layer. So for this reason, thermal bridging does occur around the perimeter of the window, and we can see cooler interior surface temperatures for that reason, which could be a indicator of thermal asymmetry, which we talked about, could create discomfort, and also potentially, if it's significant enough, could create condensation. In the example on the right, we've now set the window all the way inboard, but the same problem persists. The window is out of alignment with the insulation in the wall. And so again, we're experiencing significant heat transfer between the window and the wall assembly, and we're compromising the thermal performance of this install. The image in the middle is the just right condition. Here we can see that our interior surface temperatures are maintained throughout the wall and window install, and that our exterior cooler temperatures are also where they're supposed to be outboard of that thermal control layer and of that assembly. So in this case, we'll be able to maximize the installed R value or reduce the installed U value of the fenestration element and make sure that we're optimizing our performance and reducing the risk of thermal bridging. So the same principles apply to skylights. Here we see the Lamlux FE skylight, a very similar section to what we looked at previously. The Lamlux FE skylight is thermally continuous, so we can see that for the most part, there's no thermal bridging occurring through that assembly. In this example, we can see that the insulated curb of the skylight is again embedded in the exterior insulation of the roof structure. And we can see for that reason that this install is thermally continuous. Again, our interior surface temperatures are maintained throughout the roof opening and our exterior temperatures. So very little thermal bridging occurring either through the skylight assembly or between the skylight and the roof. So in order to optimize thermal install values, the first step would be utilizing a thermally continuous solution, right? If we don't have a thermally continuous solution, I won't say it doesn't matter how we align the window or skylight because there still will be performance differences in where it's placed. But overall, the solution is not going to provide for thermal continuity, and so so we will experience some heat transfer over the opening. Once we have specified a thermally continuous solution, we just want to align the thermal control layer in the skylight with the thermal control layer in the roof, and those insulated curves that I mentioned make that part quite simple. Thinking a little bit about U values and some product considerations for fenestration. U values for a window, door, or skylight are a weighted average of each element or each material in the window or skylight assembly. Generally speaking, the U value for the glass on any window, door, or skylight is going to be significantly less than the U value for the frame. So when we are sizing our windows or our skylights, we want to consider this, and we want to consider the fact that larger skylights, which will have the frame representing a lesser percentage of the overall skylight assembly as compared to the glass, will generally have a lower U value than smaller units. So in addition to the glass and the frame, we also want to be considering the spacer. For a high performance solution, we want to be selecting something that has warm edge spacer, a spacer made from a non-conductive material, which will prevent heat transfer from occurring between the frame and the glass. So what does this look like for skylights or for a skylight assembly? Again, here looking at a Lamlux FE, which is a thermally continuous solution that virtually eliminates thermal bridging. We can see the triple layer glazing with exceptionally low U values. In addition, this glazing always is specified with a warm edge spacer, so we can be confident that we're mitigating thermal bridging between the glass and the frame. The frame itself is aluminum at the exterior, but insulated continuously at its core. So we're reducing or mitigating heat transfer through that frame, which is going to significantly reduce or almost eliminate the impact or possibility of condensation, as well as maintain consistent interior surface temperatures. And then finally, these skylights are prefabricated on insulated curbs, which will ensure that we are thermally continuous from the skylight to the surrounding roof. If we specify a solution that's not thermally continuous, we can see a thermal model such as what is shown here on the left. Here we can see that right at the connection of the skylight to the curb, there's significant heat transfer occurring. It looks like the cold temperature or the warm temperatures are making their way through this joint, and that there's definitely heat transfer at that location. As mentioned, when this occurs during the winter, we can have the interior surface temperatures of the skylight become quite cold. And if they do reach a cold enough temperature and the warm, moist air from the interior then comes into contact with that surface, we'll see what we have here on the right, the possibility of condensation. Many manufacturers don't even plan to eliminate heat transfer. They basically admit that their skylights are not thermally continuous and that they do contain thermal bridging. And instead of preventing condensation, they just plan for it, often by providing interior gutters where condensation might occur, which weeps to the exterior via weep holes in the skylight assembly. This sort of skylight solution is obviously quite problematic for high performance buildings as it introduces thermal bridges and also compromises air control. So now I want to get into an example of how skylights affect the energy balance of a building. So again, as I mentioned in the beginning of the presentation, energy balance or energy balance calculation is basically summing all the heat gains in our building, convection, conduction, and radiation, as well as any interior gains that we might experience from appliances or electronics and that sort of thing. And then we're also deducting from that sum of heat gains, heat losses. And basically the energy balance or the sum of all our heat gains and losses will help us determine how much heating or cooling we need to offset heat transfer that might occur. So for this example, we're going to be looking at this beautiful rectangular prism of a building, masterfully created in MS Paint. This building has a footprint for our purposes of about 200 foot by 200 foot. And these skylights, which are represented here by these smaller rectangles, 36 of them total at 38 inch by 38 inch. So the total glass area for this example is 323 square feet, which is less than 1% of the overall building envelope. So over the next several slides, we're going to be looking at the impact that these 36 skylights have on the energy balance or energy demand of the building. So let's look at some data here. First, we're looking at the effect of the skylights in our hypothetical building during the winter. And as I mentioned, in New York City, in New England, and in much of the United States, we are in a heating dominated climate. So most of the operational energy that our buildings use is used to generate heat. So we're looking here at the effects that the skylights have on heat gain and heat loss and energy balance in the winter months. And each column in this chart and the corresponding table below represents a specific skylight assembly as labeled along the x-axis. So on the far left, we can see a double pane skylight solution. It's not thermal bridge free. It doesn't have curb installation, has a relatively high U glass value. So in this case, in the winter, we're going to see heat transfer via conduction through our skylight assembly because it's not providing great thermal protection. And we're going to have significant heat losses through the skylight assembly for that reason. Now, these heat losses will be partially offset by solar gains or the radiation that we receive through the glazed surface. But in this case, we can see that the heat losses greatly outweigh the solar gains, and we're going to have to generate heat mechanically to offset those heat losses and to ensure a comfortable interior. As we move through these columns, we improve the performance of the skylight steadily, first by reducing the U glass value, then by providing for a thermal bridge-free solution, and then by adding curb installation and further reducing the U glass value. And as we improve the thermal performance of the skylight assembly, we can see that we're reducing conductive heat losses, we're maintaining the solar gains, and we're able to get to a point where the conductive heat losses are less than or roughly equal to the solar gains. And in this column, which I have boxed out for you here, we can see that the solar gains are roughly equal to the heat losses, and so the skylights will have a net neutral impact on the heating demands for the interior. We can then go one step further, going to these advanced components you see on the right, which have a higher solar heat gain coefficient of about 50% as compared to 30% for the previous columns. In that example, once we would increase the solar heat gain coefficient, we're able to bring in more heat via radiation, increase our solar gains, and able to have more solar gains or greater solar gains than conductive heat losses. In those cases, we're actually able to get free heat from the sun. These solar gains will allow us to offset our heating demands and thereby reduce the carbon output of our building. So here's the data that corresponds with the charts I just showed you. So again, we can see in this table the different types of skylights in the leftmost column. And we can see here for the first example, we're looking at the triple pane with conventional spacer. In this case, because there's so much more conductive heat losses than solar gains, the heating demand for the building will actually increase as we have to generate mechanical heat, about 6% additional mechanical heat in order to offset our conductive heat losses. But as we improve the performance of the skylight, thereby reducing the conductive heat losses. We are able to get to a point where they are roughly equal to the solar gains. And that's what I said earlier will be a net neutral impact or 0% effect on the heating demands. We then take it one step further, increase the solar heat gain coefficient, and we're actually able to get to a point where we're reducing the heating demand of the interior by about 4%, thanks to the skylights, and thereby achieving that benefit of energy savings that I mentioned early in the presentation. However, in most climates, definitely New York City and most of the United States, in addition to a heating season, there's also a cooling season, right? When we're in the summer or even in the spring in some cases, we're generating cool air mechanically in order to maintain interior comfort. And we want to also consider the effect that skylights have on the energy balance during that cooling season. So we're going to look at the energy balance first, considering conductive heat transfer, and then we're going to look at the energy balance for radiative heat transfer in the slides that follow. So again, looking at a table here, the same 6 skylight examples. As you can imagine, as we move through our table here and improve the performance characteristics of the skylight, we're reducing conductive heat gain in the summer in the same way that we were reducing conductive heat gain or heat loss, I should say, in the winter. And we're actually able to significantly reduce heat gain by conduction by about 57%, just by going from some of these lower performing solutions to a more advanced component. However, in the summer, we also need to consider that our heat gains are not only coming from conduction, they're also coming from radiation. Here's a funny image I like to show of some of my colleagues in our old office before we relocated, observing the solar eclipse through one of our skylights. We didn't necessarily have effective shading for our skylights in this space, and so the effects of radiation and the discomfort that those effects create were definitely perceivable. And I think this image does a nice job of just illustrating how much radiation that we received from the skylights on our roof. So I don't have a chart for this data, but we can see here the impact of radiation on our heating demand during the cooling season. Sorry, on our cooling demand during the cooling season. In our lower performing solutions, we are getting a certain amount of solar gain due to the 30% solar heat gain coefficient. When we increase that solar heat gain coefficient to 50% to reduce our heating demand during heating season, we're also going to increase our cooling demand for the same reason during cooling season. For this reason, we have this final row here at the bottom of the table, advanced component with summer shading. This will be sort of the best of both worlds. By utilizing shading, ideally at the exterior, we can significantly reduce heat gain when we don't want it during the cooling season, and thereby reduce the total heat gain by radiation by about 33%. So we're not quite getting to net neutral or net positive effect from our skylights in this cooling season. That would be impossible. But we are able to significantly reduce the impact. And since we're using more energy in a heating dominated climate during the heating season, since we are able to reduce that energy demand, we should still have an overall reduction in heating demand throughout the full year. So I want to wrap up here with a case study of our new office, 475, relocated about 2 months ago at the end of February to a masonry building that you see shown here, the middle structure, which is just a few blocks from our old space. This masonry building was originally constructed in 1886 as a residential space on the top 2 stories over a retail space in the garage below. It was a wagon house at one point. It stored ice cream trucks for a while, and then it was a parking space essentially when we purchased the building in 2023. So our goals for the renovation of this building were to provide for an office space using largely existing masonry and then newly installed timber structure via nail laminated timber and timber joists. And also we wanted to achieve Pass certification both via PHI and FIAS, which obviously required careful optimization of the enclosure. Now, this enclosure did present some unique challenges because the new building was in the middle of the block as opposed to on the corner. We do have party walls, as you can see in the image on the right, with the building just adjacent to us on the right side of this image, and then also for half of the building on the left side of the image, as well as the back of our new office building. So because of these party walls and because we shared those walls with neighboring structures, we weren't able to use windows at those locations to bring in natural light. Similarly, at the front of the building, we have this existing residential space, which is also preventing the possibility of windows in the front of our office, which is shown here in the hatched yellow. So for this reason, we had to rely on skylights for natural light, and we actually modeled our building type. Our passive house consultant modeled the amount of illumination that our space would receive by the few windows that we were able to utilize, as well as the skylights. The modeling tool that we used for this exercise was spatial daylight autonomy, which basically indicates how much of a space is receiving certain amounts of illumination throughout the year. We were able to get to a point where we were quite happy with the results that the skylights would provide in terms of access to natural light at the interior. And as you can see in the image on the right, the space is quite bright, quite well lit, because we were able to utilize skylights as an alternative to windows in this application. So I think that this project in particular does a really nice job of introducing some of the skylights I talked about earlier in the presentation. We only have the Lamlock skylights, not the background skylights. It's our new office, so I'm going to talk primarily about them and how we use them in the structure, and then also talk a little bit, just to introduce the background products at the very end of the presentation. So the first product I want to introduce to you is the FE Circular, which is one of our curb-mounted unit skylights. So these unit skylights are pre-assembled. They come with everything you see in the section drawn on the right. Insulated glazing, thermally broken and insulated aluminum profiles, and then insulated curbs. So we'll talk a little bit about that in a second. FE Circular in this case was chosen just because we think it provides a nice design element, the nice circular geometry. And it's actually installed over a two-story atrium right above our entrance, so it brings natural light to both stories of the building, as opposed to just the top story. So these FE curb mount skylights are available in a few different varieties. I'll talk about that next. But just to kind of give some of their basic properties, as I mentioned, they are pre-assembled, so they arrive ready to install. They have typically triple pane glazing with exceptionally low U values, suitable for passive house certified projects, such as the EnerPHit certification that we're looking to achieve on our new office. They have a thermally broken frame, which you can see here in section in the bottom right. Also, thermal models given here. And again, we can see that the heat transfer through this assembly is largely prevented. And they're prefabricated on insulated curbs in standard sizes, but also available in custom sizes for attachment to a site-built curb. These FE skylights can be fixed or operable, but they are intended primarily for flat or low pitch applications up to about 25 degrees or 612. Looking a little bit closer at these curves that I keep referencing, primarily because I think they're a pretty unique feature of the Lamlock skylights that do allow for excellent thermal control in high performance enclosures. These curves are available from Lamlocks in a variety of different heights. You can see the K curves shown here in the top left, which are available with a height of 6, 12, 16, or 20 inches and have a wider splay to allow light to penetrate deeper to the interior. And then we also could supply a Fit 6 curve, height of about 8 inches, shown in the bottom left, which has a narrower splay, which could be a design choice for certain applications. The height of the curb for these Lamlocks FE skylights is going to be dictated primarily by the thickness of the roof assembly. Because as we can see in the section drawn on the right, ideally, in a best practice install, this Lamlocks curb is embedded in that exterior insulation layer of the roof to provide for continuous thermal control. And we need to maintain 6 inches of clearance from the roofing or the flashing layer, the layer where water will collect, to the top of the curb. So for buildings that have thicker exterior insulation, we'll have to have a taller curb to maintain that clearance. But in this case, we were able to utilize, as shown in the section drawing, the Fit 6 curb with a height of 8 inches while still maintaining that 6-inch clearance requirement. These FE skylights are available in several different varieties. There's the standard FE, sort of our bread and butter unit skylight, available in rectangles up to about 4.5 feet by 10 feet, or about 6 feet square. We can see one installed here on a brownstone in Brooklyn. We can see that the frame in this case is brushed aluminum. That frame, however, can also be powder coated in any RAL color. Image on the right, I think, shows a really nice install here with the skylight curb embedded in the roof assembly, and then flashed continuously from the roof to the curb, providing for excellent water control as well. In addition to the FE, there's also the FE 3-degree, which has virtually the same assembly, but also includes an integrated 3-degree slope for roofs that are particularly low slope or flat. This can be a nice choice to ensure that you're allowing for efficient shedding of water and snow, and that water or snow will not pond or collect on the surface of the skylight over time, which can create additional requirements for cleaning and maintenance. Then there's the FE exit hatch, which is particularly relevant, I think, in urban applications. In New York City, it's a requirement for many residential buildings. But this is basically an FE equipped with pneumatic pistons and a lockable latch, as shown in this image, that opens manually to an angle that allows for you to climb out of the skylight and onto the roof. And this sort of solution is typically utilized over a ladder. There's the FE circular, which is the product featured in our office. Again, a prefabricated solution only available in standard sizes, up to about almost 8 feet or about 7.5 feet in diameter. A nice design element for applications that need maybe, or applications or projects need a little bit something funky or something different. We have it in our office here, and it's a really nice eye-catching fenestration element. Here is that same FE circular skylight shown on a library project out in the Bay Area. This is the Pleasant Hill Library. We find that these circular skylights are ideally suited for these sort of institutional commercial applications, although they're also perfectly suitable for residential applications as well. So the next product group I want to talk about is our roof access skylights, which are represented on our new headquarters via the Comfort Swing, which you see here, another product from BuildingBlocks. This skylight has a very similar assembly to the FEs that I showed previously. So it has that same continuously insulated curb, which in this case you see we powder coated 475 blue. The skylight itself has triple layer glazing as well and is prefabricated on this insulated curb, which you can see partially protruding from the roof in the image on the right. This curb has an integrated slope, again, to ensure for efficient shedding of water and snow. Within that curb are two motorized pistons, which again, you can see in this image, which open the skylight outward via a hinged edge. This is, of course, a motorized solution that allows for roof access, ideally over a staircase. It's available in two sizes, about 40 inches by about 118 inches, and then about 40 inches by about 137 inches. Unfortunately for this product, there are no custom sizes available. And the final product I want to talk about through the lens of our new 475 headquarters, the BuildingBlocks PR60. This is a glass roof system, otherwise known as a mullion and transom system or a knockdown system. Essentially, it's a curtain wall from the roof delivered to the job site as a kit of parts, which includes the triple layer insulated glazing units, the IGUs, the thermally broken aluminum profiles, which are continuously insulated, and then the insulated flashing connections to the existing structure, which will again provide for very high levels of quality control for thermal control between the skylight and the roof assembly itself. You can see the details for the skylight or the PR60 install on the right. These are from the BuildingBlocks shop drawings, which they provide for every skylight and for every PR60. In this case, you can see that the profile itself is thermally broken. We'll look at that thermal protection and how that is achieved in a second here. There's this insulated flashing connection, which is going to protect that profile and provide thermal control outboard of that profile. And then we also have this mineral wool, which is supplied as part of the BuildingBlocks scope, which is again going to prevent heat transfer through the aluminum profiles. In this case, we installed the skylight itself over an insulated stud cavity, essentially, which served as our curb. And for that reason, this insulation is in alignment. The insulation in the skylight itself is in alignment with the insulation in the curb, and we have excellent thermal continuity for this install. This PR60 also featured a vent flap, which you can see in the bottom of the image on the left, and also shown in section in the drawing on the right. The windows on our office needed to be installed with fire protection windows outboard of them. And since there weren't fire protection windows able to provide for past levels of performance available, we basically have two windows installed, and the fire protection windows are not operable. So the only way that we were able to bring in natural air, fresh air via natural ventilation is through the roof access skylight, the Comfort Swing, and then also via this ventilator flap as part of the PR60. So just looking at the PR60 in a little more detail here, you can see in the right another thermal model of the assembly indicating that there's very little heat transfer, virtually no heat transfer occurring through the PR60. Again, so there's very little risk, virtually no risk of condensation occurring, and there's no sort of gutter or weep holes required to manage moisture that might occur during condensation. These skylights, PR60s, are fully customizable, so they can be installed on slopes as low as 2 degrees or as steep as 90 degrees, and we can integrate sloped glazing with vertical glazing as part of the PR60 assembly. We are able to provide very large glass fields up to about 6 feet square or 10 foot by 3 foot. So really nice sight lines, particularly when you consider the narrowness of the PR60 profiles. And then because these skylights are more technically challenging, both in terms of engineering and also installing, 475 does provide a suite of services to support their successful implementation. Looking at the PR60 assembly a little bit closer, here we can see a cross section through one of the profiles, triple layer glazing unit shown on the right, again, always with a warm edge spacer. The interior pane of all Lamelux skylights is always laminated. The exterior pane is always tempered. This is providing for fall-through protection and preventing breakage to or cracking to the greatest extent possible. You can see within the profile itself is this thermally optimized insulation core, basically a foam strip that runs continuously along all the profiles and is the primary measure by which the profiles prevent thermal bridging. At the interior and the exterior of this insulation core, we can see these EPDM gaskets. The EPDM gasket at the exterior is our primary air and water control layer. So because this PR60 relies on a gasket as opposed to silicone for water tightness. We do call it a dry glaze system because there's no wet silicone required. These dry glaze systems require more maintenance over time, while silicone connections can break down and crack and degrade over the lifetime of a product. Gaskets are much more durable and require much less maintenance to maintain. The secondary gasket at the interior is to collect any moisture that might penetrate through the exterior gasket. Because it is a dry glaze system, particularly during high pressure storm events, you can see trace amounts of water make its way behind that primary gasket, in which case it'll come in here through the assembly and collect in these interior gutters of the secondary gasket. These gutters or channels, so to speak, are outboard of our air control layer. So they're able to passively ventilate or passively drain water to the exterior without compromising air tightness. The profiles themselves are always 60 millimeters wide. That's where the product name comes from, PR60. They're aluminum and can be powder coated in any RAL color. And the depth of the profile will vary depending on the static loads of the skylight assembly. As shown here, with various different heights, the profiles, but with the 60 millimeter width or 2 3/8 inch width maintains. The PR60 is a structural glass roof system, so it can be self-spanning up to about 20 feet. And in those self-spanning applications, the only supplementary structure required would be the perimeter curb structure. Here again, just looking at a section of the assembly, pretty much what we saw previously, but we, in this case, have, again, triple layer glazing, thermally broken flashing, in this case, with foam insulation pre-attached to this aluminum weather sheet, as Lamlos calls it. Just below that is this mineral wool layer, which is tied in place with an EPDM membrane, the primary flashing layer at the perimeter of the PR60, which that mineral wool insulation prevents heat transfer from occurring through this aluminum profile. These PR60s can be curb mounted. They can also be mounted to a vertical wall assembly, or in this case, flashed to that assembly, in which case those same weather sheets, instead of bending down over the curb, bend up to align with the wall, and then can be capped with some sort of counter flashing just above. The PR60 is extremely flexible in its design, which is really nice when designing really unique or more technically challenging skylight assemblies. Here you can see PR60s in ridge roof application, a pyramid roof, a barrel roof, and also ideally suited for very large glass roofs because they can be self-spanning up to spans of about 20 feet. So a few additional examples of PR60s outside of our headquarters. Here is a photographer's studio, not too far from our office in Fort Greene in Brooklyn. I like to show this project for a couple of reasons. One, it utilizes a really large, nice glass field, which is going to provide excellent natural light at the interior and provide really nice sight lines to the skylight itself. And as you can see here in the image on the right, this PR60 actually has sloped glazing at the roof and then also vertical glazing at the wall. And I think this image of this project is a really nice job showing how those two elements of the PR60 can be integrated seamlessly and supplied as part of the same scope. Here we can see one of my favorite projects that I've gotten to work on. This is the Poder headquarters in Chicago, Illinois. The Poder headquarters is an immigration center, so they provide education services for immigrants looking to enter the workforce in the United States. The architects of this project, FTP Atelier, designed this really funky, interesting extended pyramid on the roof, as you can see here, over an existing opening, about 30 feet in length by about 10 feet in width. This extended pyramid had some really unusual or uncommon load distribution due to its geometry, and it was a bit of a challenge for Lamlos to engineer. However, in the end, we were one of the only manufacturers that were able to realize its design as part of the PR60 glass roof system without really altering it to any significant extent. Here it is showed at the interior. As part of the design priority for this project, they wanted the different facets of the skylight to match the four different colors of the Podair logo, blue, red, green, and yellow. So as you can see here, we utilized frit, both ceramic and digital prints, to create that effect. And here's another nice project we did out in Columbus, Ohio. Here we have a very large PR60 glass roof over seafood restaurant. I think this image does a really nice job demonstrating the benefits natural light can have for commercial space. You can see how warm and how welcoming the space is and how bright the colors at the interior are because of the natural light flooding the space. Some exterior images. Here you can see that we have a variety of different connections, different sort of junctions within the skylight itself. The entire glass roof was supplied as a PR60, including this little bump out at the front, which also features a vertical gable, which again, the PR60 could accommodate. So that kind of wraps up the case study. I just want to mention we also supply skylights through FACRO for particularly pitched roof applications for slopes typically greater than 25 degrees. These skylights are also pre-assembled, and so they are delivered ready to install for the most part. They don't require any assembly on site, so to speak. They do not have insulated frames, but they have cross-laminated timber frames, which are, because wood is non-conductive and because we have this cross-lamination, going to prevent most heat transfer or significantly reduce heat transfer from occurring through the frames itself. They have, again, triple pane glazing, and they're typically supplied with insulated flashing kits, which vary depending on the roof type to ensure thermal continuity between the skylight and the surrounding roof construction. These stock road deck mount skylights are available in a few different varieties. So we have the FNP fixed, which is often available from our inventory with shorter lead times. And then we also have two different options for operability, the FTT U6 or U8 center pivot skylights, and then the FPP top hung skylights. The Wemlock skylights, as I mentioned earlier, are curb mounted, but these FACRO skylights are deck mounted. So what that means is that they're not elevated over the roof structure using a curb. They're installed essentially directly to the roof deck layer or to the battens in the case of a ventilated roof, which does provide a lower profile, which is sometimes more desirable, particularly for pitched roof projects or smaller residential projects. And here we can sort of see how that skylight would be embedded or installed in a timber roof structure. And one last product to send you home with. Certainly very specific, but a question that I get pretty often is, can we supply walkable skylights? The answer is yes. FACRO does have a walkable skylight product available available in sizes up to about 4 foot by 4 feet with a frame and glazing that is designed and engineered to sit flush with the roof deck, ideally suited for walkable or accessible roof deck applications. So thanks again, guys, for taking the time to learn a little bit about our high-performance roof daylighting products today. I hope that you learned something. I'm happy to stick around and answer any questions. You can see my contact information here. If you'd like to get in touch, we're definitely happy to recommend solutions, provide consultation, estimates, etc. So look forward to hearing from you, and